the atomic number of atom or that nucleus. Protons and neutrons are collectively called nucleons, and number of protons is nothing but A minus Z, where A is number of nucleons. So if A is number of nucleons, that is protons plus neutrons, then your A minus Z, where Z is the atomic number or number of protons, then number of neutrons will be nothing but A minus Z. So, and electrons revolve around the nucleus in a specific orbit and it is negatively charged. The number of electrons that surrounded the nucleus must be equal to the number of protons in the nucleus to make it having zero charge or electrically neutral. Otherwise, a small positive charge will experience enormous force using the formula F is equal to minus 1 Q1 by Q2 by R square R cap, and the constant will be 1 by 4 pi epsilon 0, which is very large. So F is equal to 1 by 4 pi epsilon 0 Q1 Q2 by R square R cap. So if your Q1 and Q1 positively charged, then plus multiplied by plus multiplied by plus will be plus, and it will be a repulsive force. And similarly, if there are two electrons, minus multiplied by minus will be plus, that is also a repulsive force. And if one is minus and another is plus, then it will be minus and it will result in a attractive force, which I have discussed in first year in the quantum mechanics class. So since the electrons and protons are equal in numbers, the atom is neutral, and the structure of atom is basically the classical concept is given by Niels Bohr, and this can be shown as in the screen. There is a nucleus consists of nucleons, that is protons and neutrons, and electrons revolving around the nucleus in circular orbits. And the charge of proton will be 1.6 into 10 to the minus 19 coulomb, you know, and that of electron is minus 1.6 into 10 to the minus 19 coulomb. So charge of the proton is negative of that of the charge of electron, and the value is same. And the mass of the proton will be 1.672583 into 10 to the minus 27 kg, you know, and it can be expressed in atom mu, atomic energy unit, and it is around 1, and that the neutron mass is also around 1. So mass of the proton will be 1.00727 atomic mass unit, and that of neutron is 1.00865 atomic mass unit, and that is 1.674888 into 10 to the power minus 27 kg. But the mass of the electron is very less than that of mass of the protons or neutrons. It is 1.0005486 atomic mass unit, and it is 9.1095 into 10 to the power minus 31 kg. And the average radius of the atom is less than 3 angstrom. 1 angstrom is 10 to the power minus 10 meter. And the radius of the nucleus is around 1.2 fermatometer. So where Fm is equal to 10 to the power minus 15. So this is the Bohr's picture. Then there is a energy mass equivalence due to Einstein, and there is a unit of energy electron volt, which is 1.6 into 10 to the power minus 13 joule, or 1.6 into 10 to the power minus 13 joule is equal to 10 to the power minus 6 eV, or 1 eV is equal to 1.6 into 10 to the power minus 19 joule. You know, the electron temperature, the proton temperature are expressed in electron volts. So this is, so how it happens, mass energy equivalence. The mass of the particle are expressed in atomic mass unit or U, which is a very small fraction of gram. So how a gram is expressed as a atomic mass unit. As per Einstein's mass energy equivalence principle, energy and mass can manifest mutually and both could be expressed in the same unit using the conventional definition of energy and mass. So Einstein gave a simple relation: energy is equal to c square times mass, where c is velocity of the light in vacuum, that is 3 into 10 to the power 8 meter per second. So it has been established in nuclear physics experiments that any energy gain or release is accounted for by a loss in mass, exactly according to Einstein's relationship. So you can say 1 U is equal to 931.5 mega electron volt by C square. Mass of the proton is 938.272 mega electron volt by C square, and mass of neutron is 939.565 mega electron volt by C square. And I have told you earlier 1 U is equal to 1.6605 into 10 to the power minus 27 kg. Then your nucleus is represented by a symbol X superscript capital A subscript Z, where A is nuclear number and Z is atomic number, and Z represents the number of protons and A represents the number of nucleons. And your X minus A is also another representation. So you can represent an uranium isotope as U superscript 238 subscript 92. That means, or you can write U hyphen 238. So 238 is atomic mass number, and it is the atomic mass number of uranium is 228. That means in uranium atom, in normal uranium atom, you have your 238 protons and 238 nucleons. 238 nucleons, one proton plus neutron is equal to 238. And you can also write U superscript 238, and in some representation the atomic number is not written. Only the number of nucleons or mass number of nucleon or mass number is written. So 238 is mass number that represents number of nucleons. Similarly, electron, the mass of electron is 0, the mass of proton is 1, and the mass of neutron is 1. So electron can be written as 0 minus 1 e, where minus 1 is its charge, 0 is its mass. Proton is represented as 1p1, where its mass number is 1 and charge is plus 1. And neutron can be represented as 1n0, where 1 is its mass and 0 is its charge. You know all these things. And species of nucleus with a given capital Z and capital A, you can refer, and you have a different nuclide if Z or A is different. Different nuclides have different nuclear properties. You know isotopes in your chemistry as well as physics class. What is an isotope? Atom of the same element. Same element matlab same Z, same atomic number, but mass number differs, are called isotopes. Suppose we consider an atom hydrogen. So in a hydrogen, your Z is same. The isotopes of hydrogen, Z is same. That means atomic number is same. Number of protons or electrons are same. And you have hydrogen, deuterium, and tritium. In these three, in hydrogen as well as deuterium as well as tritium, your atomic number is 1. But the mass of hydrogen is 1 mass number of hydrogen is 1, mass number of deuterium is 2, and mass number of tritium or tritium is 3. That means in hydrogen you have 1 proton and no neutron, 1 electron. In deuterium you have 1 proton, 1 neutron, and its charge is charge of the nucleon is +1, and here there is 1 electron. Similarly, in tritium, you have 1 proton, 1 electron, and 2 neutrons. So deuterium, tritium, and hydrogen are isotopes of hydrogen. Similarly, you can have different isotopes of uranium. So you know atomic number of uranium is 92. So uranium atom has 92 number of protons and 92 number of electrons around the nucleus. And it might have different neutrons. So 141 neutron in an uranium atom is one isotope. 142 number of neutrons in an uranium atom as another isotope. And 144 number of neutrons in an uranium atom is another isotope. So 144, 143, and 142. So if an uranium has 142 number of neutrons and 92 number of protons, the mass number will be 233. If the uranium has 143 number of neutrons and 92 number of protons, the mass number will be 235. And if the uranium atom has 92 number of protons and 144 number of neutrons, its mass number will be 238. So the isotopes can be written as uranium 233 92, uranium 235 92, and uranium 238 92. So 233 92 represents 92 number of electrons and 141 number of neutrons. 235 isotope represents 92 number of protons and 143 number of neutrons. Similarly, the third isotope has a 92 number of protons and 146 number of neutrons. So 146, 143, and 141. Three isotope contains these much neutrons. Isotopes have the same chemical properties but can have very different nuclear properties. So the chemical properties of the atom, the chemical property of the isotopes are due to their atoms and their atomic number, but the nuclear properties depends upon the nuclear number. So since the nuclear number differs in the isotopes, they have different nuclear properties, but they have same chemical property. So what is nuclear size? The radius of an atom is the distance between the center of the nucleus and the outermost electron orbit. So you can see here in the table 1, here, which we have discussed, proton, electron, neutron, so on and so forth, atom and nucleus. That atomic size is much larger than the nuclear size. You can see here, what will be the nuclear size? The nucleus, radius of the nucleus is around 1.2 FM. So, but the radius of the atom is 3 angstrom. Angstrom 10 to the power 10, minus 10, 10 to the power minus 10. But FM is 10 to the power minus 15. So 10 to the power 5 orders large, the atomic radius. than that of the nuclear radius. So an atom holds a large unoccupied space, which was discovered during the Rutherford experiment. 10 to the power 5. 10 to the power 5 matlab 1 lakh times. So if the nuclear radius is 1 centimeter, then the atomic radius will be 1 lakh centimeter. So you see, in an atom there is a huge void or unoccupied space. The nucleus occupies only a region having 2 centimeter diameter, and the electron is around 1 lakh centimeter radius away from the center of the nucleus. So there is a huge unoccupied space within the atom. And you can see that neutron is slightly heavier than proton. You can see here, the neutron is slightly heavier than proton. The neutron mass is 1.674888 into 10 to the minus 27 kg. For that of proton is 1.672583 into 10 to the minus 27 kg. So the neutron mass is slightly higher than that of proton mass. And you can see the mass of the electron is around 10 to the power minus 3 times less than that of protons. You can see here what is the electronic mass, 9.1 into 10 to the power minus 31 kg. And mass of the proton will be of the order of 27, 1.672583 into 10 to the power minus 27 kg. So 10 to the power 4 order, 27, 31. 10 to the power 4 order, but it is 9, so 10 to the power 3 order. It is 1, it is around 10, so it will be 0.9 into 10 to the power minus 30. So that is 27, 30, 10 to the power 3 orders high, so at 2000 times higher than that of the proton. So the entire mass of the atom is concentrated in the nucleus. The massive particle proton, the massive particle neutron is there in the nucleus, and the lighter particle electron is in the extranuclear region. So the mass is concentrated at the nucleus, and the volume of the nucleus is proportional to its mass and its radius by the formula R is equal to R0 a to the power 1 by 3. Kujakar's semi-empirical formula, you can find this term. So your R0 is the radius, nuclear radius, and A is the mass number. So your R can be represented as R0 a to the power 1 by 3. And R0 is the constant, proportionality constant, and its value is around 1.2 FM, 1.2 into 10 to the minus 15 meter. So the description of a subatomic system is best given by quantum mechanics. Bohr's model of atom invokes quantum concept at a basic level, but the modern models are fairly rigorous. So the revolution of electron in a fixed circular orbit is a convenient way to picturize atomic structure for a layman, though not perfect. This picture is practically accurate, not perfect, but accurate. So in quantum mechanics, you can find the orbits of the electron, orbital of the electron, S, P, D, so on and so forth. And the terminology used is probability of find the electron in a region, or eigenvalue, velocity eigenvalue of the electron, energy eigenvalue of the electron, so on and so forth. Not the value of energy of the electron or velocity of the electron or the position of the electron. Then what is how you can get the nuclear force? In classical mechanics, you are well acquainted with the gravitational force, and F vector is represented as minus G m1 m2 by r square r cap. So minus is due to the attractive force, and m1 m2 are always positive, and the value of G, you know. r is the distance between two particles, or radial distance between the two particles. Similarly, the electrical force, you have the expression F vector is equal to 1 by 4 pi epsilon 0 q1 q2 by r square r cap. Here there is no negative sign, because the nature of the force will depend upon the the value of q1 and q2. If both are negative, then it is positive and a repulsive force. If both are positive, then it is positive, a repulsive force. If one is positive, another is negative, then minus sign, and it is an attractive force. Then nuclear force. How does a tiny nucleus hold so much nucleon together, including positively charged protons? If in a nucleus you will consider only nuclear region, then there are neutrons and protons. Neutrons are neutral particles, protons are positively charged particles. So Q1 is positive, Q2 is positive. So your force is repulsive. In an uranium atom, 92 number of protons. So enormous repulsive force in the nucleus. Even in a carbon atom or in a nitrogen atom, there are enough electrical repulsive force to tear the nucleus apart. But how nucleons held together tightly in the nucleus? Initially, we are of the view that number of proton and number of electron make it neutral, and your the atom is electrically neutral and there is no force. But you see that electron is far away from the nucleus, 200 times the smaller mass, and the distance is around 10 to the 5 times of that of the nuclear radius. So a strong nuclear force is predicted, which is characteristics of nucleons only. Nuclear force referred to as short range force, unlike that of gravitational or electrical forces, and is effective only within the nuclear dimension, that is 10 FM, 10 into 10 to the minus 15 meter. It is attractive and is much larger than the electrostatic repulsion between the protons. So these can held together, the protons and neutrons are held together. This means that even a proton attracts another proton, however, distance is less than nuclear force diminishes. At short distances, the electrostatic repulsive forces between protons show up only at distances where the nuclear force becomes weak. When you come to the electrons in an atomic orbit, there you have no nuclear force because it diminishes and it falls rapidly as the distance increases. And nuclear force becomes weak and cause some instability to the nucleus. Hence, you can encounter radioactivity. As the number of protons increases, the mass number increases. The stability requires presence of more neutrons than protons in the nucleus. Therefore, for most nuclei, excluding a few lighter ones, the number of neutrons is greater than the number of protons. This is because addition of neutrons does not involve repulsion and enhances net attractive force, because neutron is a neutral particle. An atomic nucleus has exceptionally large matter density, since a large mass is packed in small volume. The mass of neutrons and protons are 200, around 1 800 or 2000 times larger than that of the electron. Taking the nuclear mass and the radius of the nucleus with R0 is equal to 1.2 Fm, the density of nuclear matter comes out to be the order of 10 to the power 14 gram per centimeter cube or 10 to the power 17 kg per meter cube. The nuclear mass and volume are independently proportional to A, and so nuclear density does not depend on it. So there are some worked out examples. Calculate the density of nuclear mass with nuclear mass 1.67 into 10 to the minus 24 gram, where R0 is equal to 1.2 Fm. So you have the formula R is equal to R0 A to the power 1 by 3. So your volume can be written as 4 by 3 pi RQ. 4 by 3 pi RQ. So RQ is equal to R0Q A. So by substituting these values, you have your V or volume is equal to 7.24 into 10 to the power minus 39 A CMQ. And mass of the nucleus is equal to mass of the nucleon multiplied by A, which is nothing but 1.67 into 10 to the power minus 24 into A gram. Then density of the nucleus is mass by volume, which will be nothing but 1.67 into 10 to the minus 24 multiplied by A, atomic number, gram, 7.24 into 10 to the power minus 39 A centimeter cube. By dividing these two, you have 2.3 into 10 to the power 17 kg by meter cube. And the nuclear density is independent of A, since the nuclear mass and nuclear volume are both proportional to A. Then your nuclear charge. So you know, nucleus is having protons and neutrons. Protons are having positively charged. So nuclear charge, net nuclear charge is positive and is nearly constant from the center to the periphery, where it shows a fall, rapid but not abrupt, indicating a diffusion, not sharp surface, diffuse surface. So the nuclear charge density distribution with respect to radius rho, which is a function of r, is given by rho r is directly proportional to rho 0 by 1 plus exponential small r minus capital R by A, where r is radial distance, A is diffuseness parameter, which determines the extent of falling portion of the graph taken to be 4A. R is such that rho r is equal to rho 0 by 2. The variation of charge density with radius is shown in the figure. In the y-axis you have rho, and in x-axis you have r. Then mass and binding energy. So what binds the nucleons together? Nucleons are held together within the tiny nuclear volume by a short-range nuclear force. The energy that holds the nucleons together is known as nuclear binding energy, or sometimes it is written as BE, and is equal to the energy needed to separate the bound nucleons. So we can say that the nucleus loses or releases some energy when the nucleons are packed in, and unpacks if the same amount of energy were given to it. Obviously, this energy must be accounted for by loss or gain of some mass. So release of energy during nucleon packing must be at the cost or reduction of some mass. This is borne out by observed fact that the net mass of any nucleus is less than the sum of masses of nucleons therein. The difference or the reduction in mass is called mass defect. And mass defect can be calculated using the formula del M is equal to ZMP plus A minus Z Mn minus capital M subscript A, where Ma is nuclear mass, Mp is proton mass, Mn is neutron mass, del M is in the unit of U. And the binding energy is given by del M multiplied by 931.5 MeV. So for a helium nucleus, Ma will be 4U, taking the proton and neutron masses, as we have discussed earlier. So the mass defect del M will be 0.03035 U and your binding energy will be 28.3 mega electron volt. So an electron is bound in its orbit by a few tens of electron volt, whereas every nucleon in a nucleus is bound with a few mega electron volt of energy. The masses of all known nuclei, stable or unstable, are available in standard nuclear data tables, and binding energy of any nuclide could easily be computed. Then your nuclear stability. The enormity of the binding energy of nuclei indicates the strength of the nuclear force, hence the stability. So this is shown in the curve. Number of protons versus number of neutrons. Number of protons versus n by z ratio. So total binding energy of a nucleus increases as the number of nucleons increases, though the quantum of increase for every added nucleon reduces for heavy nuclei. The stability of a nucleus is indicated by its average binding energy, that is binding energy per nucleon, or B by A. And B by A graph is plotted in the curve, atomic mass number A versus binding energy per nucleon. And you can see it increases sharply, and around 56 it peaks, that is the atomic mass of iron, which is the most stable nuclei. So similarly, iron, nickel, chromium, these are stable nuclei, and its value is around 8 mega electron volt. Then it decreases slowly, and you will arrive at 238, the maximum A possible for a atom in the curve. Then your excited states and radioactive decay. Subatomic systems can be described reliably only through quantum mechanics. A nucleus can exist in one of many well-defined discrete states that are characteristics of a given nucleus. The discrete energy states, are called quantum mechanically permitted states, are referred as energy levels. Transition from one such level to next lower level will involve release of a quantum of energy or quanta of energy exactly equal to the difference between two levels. You can see in the picture, nuclear energy level. Excited states, ground level, and in case of a gamma ray emission, what happens? So when from a excited level it comes to the ground level, then the quanta of energy released will be same as that of the energy difference between these two levels. And energy levels occupied by the nucleons in an unexcited nucleus are called bound levels. The nucleus acquires additional energy, it goes to an excited level, then comes back to the ground state by emitting energy. And radioactivity is nothing but nuclear disintegration activity in which an unstable nucleus transforms to a stable configuration. The strong force cannot hold any arbitrary nuclear configuration stable. Most of the known nuclei exceeding 3,000 in number are unstable, and less than some 300 nuclei are stable in nature. And these include the isotopes. A nucleus with inadequate binding energy is unstable. Nucleus with extra energy, that is a nuclide that still has energy left to be released, is also unstable. Such unstable nuclide disintegrate to attain stability. Stability could be reached in a single step or through several intermediate steps. The disintegration process to reach a stable configuration happens commonly through emission of energetic particles, alpha, beta, gamma, so on and so forth. However, radioactive decay can also happen through release of neutrons or through fission or splitting of a larger nuclei into smaller fragments. De-excitation from a higher energy state is also considered a radioactive process. It could happen through release of enormous energy in form of gamma rays. Unstable nuclei that exist in nature undergo natural radioactivity, and the man-made unstable nuclei are said to undergo artificial radioactivity. So let us have the alpha decay. Uranium 23892 decays into thorium 22490 plus helium. Beta decay, your neutron decays into proton, electron, and neutrino. Gamma decay, high energy electromagnetic waves. Emission of gamma ray changes neither mass number nor atomic number. So alpha particle is nothing but a helium, and your beta decay is nothing but an electron, and similarly gamma is a high energy photon. And the rate of decay can be calculated using the formula dN by dt is equal to minus lambda n, which is a function of t. And the nt is n0 e to the power minus lambda t. You know it. Then mean life. Lifetime of a nucleus can be defined as that time small t for which it lives but collapses within an infinitesimally short time dt after t. Since lambda defines the probability of decay per unit time, lambda dt gives the probability of decay in a time interval dt. So n by n0 is equal to e to the power minus lambda t gives the probability of survival or escaping decay for a nucleus up to time t. So mean lifetime of the decaying nuclide can be obtained using the formula Tm is equal to integration 0 to infinite n0 t to the power minus lambda t multiplied by lambda dt divided by integration 0 to infinite n0 e to the power minus lambda t lambda dt, which is nothing but 1 by lambda, or total lifetime of all nuclei having each living for different times by total original number of nuclei. Then radioactive disintegration versus disintegration time, remaining fraction of the parent nuclei in y-axis, disintegration time in x-axis. This is a exponentially decaying curve because you can see that n by n0 is minus is equal to e to the power minus lambda t by 2. So t half is equal to ln 2 by lambda. So it is an exponential curve. So there are different nuclear models. One is liquid model. So as the liquid drop disintegrate into two drops due to fluid instability. Similarly, nucleus can be disintegrated into two parts, and the larger nuclei is considered as a larger drop, and two smaller nuclei are the small disintegrated drops. And the formula, semi-empirical formula for the binding energy to explain this nuclear liquid drop model is given by German physicist Carl Friedrich von Weizsäcker and is known as semi-empirical mass formula. So it is EB is equal to AV A minus AS A to the power 2 by 3 minus SC Z square by A to the power 1 by 3 minus A subscript A minus 2Z square by A plus minus delta. So these terms are volume binding energy term, AV, then surface binding energy term, then Coulomb binding energy term, then asymmetry binding energy term, then pairing energy term, delta. Then another model is cell model. The cell model considers nucleus to be a potential well for the nucleons, in the sense that the nucleon coming in this region would be captured. However, the nucleons thus bound in this well occupy only permitted energy states defined by quantum mechanics. These energy states are called cells that are available for nucleons to occupy. Every cell has a limit for occupation by nucleons. Protons and neutrons occupy different sets of cells. The cell structure of each nucleide is different from other nuclei with a field, that is closed cells, of greater stability than those with small unfilled cells. This is explained remarkable stability of the nuclei with Z or A minus Z equal to the magic number 2, 8, 20, 28, 50, 82 or 126. The reason for the uranium and thorium series of radioactivity ending with stable lead 82 to 08 is that it is doubly magic nuclide, that is Z82 and N126. It must be understood that the observed stability of nuclei with magic number of nucleons does not imply that stable nuclei could be formed with any combination of magic number Z and A minus Z. So, for example, nickel is unstable. The nuclear reaction, there are some examples: reactants, products, and in between the compound nucleus. And compound nuclear reaction is shown in the screen: kinetic energy and binding energy of the neutron. Then Q value of the nuclear reaction. This is very much important. The total energy, including the mass energy, is conserved in a nuclear reaction. That is total mass of the reactant expressed in the energy unit, E is equal to mc square, plus their total kinetic energy must be equal to the total mass of the products and their total kinetic energy plus energy of the photons released. A change in the total rest mass due to the reaction will manifest as a change in the kinetic energy and vice versa. So if Mi and Mf are the total rest masses of the reactants and the products respectively, with Ei and Ef being the corresponding kinetic energy, then energy conservation will imply Ei minus mic square is equal to Ef plus mfc square, and you can write Mi minus mfc square is equal to Ef minus Ei is Q, and it is this change in Q in the rest mass energy or kinetic energy is called the Q value of the nuclear reaction. A positive value of Q indicates that the reaction has released energy, and the negative value absorbed energy. So if the Q is positive, it is an exothermic or exorgic reaction. If Q is negative, then it is endothermic or anorgic reaction. Then neutron can also react with matter and influence the energy levels, cross sections and reaction rates, and so on and so forth. Then neutron absorption. Direct reaction mechanism, nuclear interaction in most of the energy ranges in a reactor takes place through the CN mode. This means that colliding nuclear neutron is captured by the target, and type of disintegration of the excited CN decides the types of the reaction. In other words, in certain reactions, the projectile N is captured by the target to form a CN compound nuclei, which subsequently disintegrates by emitting the particle X. The reaction in which the CN or compound nuclei ejects the neutron is called scattering, which will be discussed. These are called, there are reactions in which neutron is not given back, neutron is lost. These are called capture reactions. And we can say that radiative capture, where your N comma gamma. In term of neutron absorption is also used to denote neutron capture. However, these two terms have specific individual meanings in certain contexts in the reactor physics. It will become clear when we discuss the basic reactor concepts. Then radiative capture, the N comma gamma reaction takes place through the CN mode as shown in the screen. So compound nuclei, the reactant, then compound nuclei or CN, then product. Reactant, and it will be product. Elastic scattering, and here elastic scattering through compound nucleus. Neutron inelastic scattering, when neutron is bombarded to the nuclei, the compound nucleus formed, and your product nuclei and a neutron is emitted. The neutron transmission and mean free path. So consider one speed in neutrons for intensity I0 neutron centimeter to the power minus 2 second to the power minus 1 incident on the face of a target medium of thickness x centimeter, atomic density n per centimeter cube, microscopic total cross section sigma barn, and macroscopic total cross section sigma t centimeter to the power minus 1. So neutron transmitter incident intensity, then emergent intensity shown in the screen. I think the screen is not visible. Yes, it is visible now. Then your resonance, compound nucleus energy levels and cross-section resonances, and parts of the resonance core which is shown in the screen. then Brett-Whitner mass formula. So it is sigma x, which is a function of E is equal to pi by k Gj gamma n gamma x by E minus E0 square plus gamma square by 4. And the statistical spin factor Gj, which means the probability that the compound nucleus spin is capital J, is given by Gj is equal to 2J plus 1 by 4L plus 2. And you can have the cross section versus energy graph, where you can see the energy variation of cross sections for different nuclei, and there is drastic differences for different nucleides. There are also some general trends. Generally, cross section for non-threshold reaction is smooth up to some energy, then has a violent variation or resonances, and again becomes smooth at high energies. The region of resonances, the resonance widths, and spacing are different for different nucleides. So are the thresholds where they exist. Then elastic scattering cross section for hydrogen, oxygen, and iron nuclei. Radioactive capture cross section for N gamma reaction for iron, uranium, and boron. There is an example. By making a reasonable approximation, calculate the radiative capture cross section of nuclei at 4 electron volt. Given its value 0.04 electron volt to be 100 barns. So sigma is equal to k by root over of E. So at 0.04 EV, k by root over of 0.04 is equal to 100 barn. So k will be 20. So sigma will be 10 barns. Then fission, NF, low energy behavior, inelastic scattering cross section for manganese and iron is shown in the screen. The neutron multiplication reactions like N2N, N3N are threshold reactions. Neutron disappearance reactions like NP, ND, NT, hydrogen, deuterium, and tritium, and N alpha are generally threshold reactions, but occur without threshold in a few cases. The cross-section curves for the threshold reaction behaves like the inelastic scattering. Such reaction, when they have threshold, are endorgic with negative Q value. So there are some terminal questions. You can go through these. Yes.
Hello, sir. What is threshold reaction?
Threshold reaction. Okay. So we have two types of reactions. One where energy is absorbed and another where energy is released. So when energy is absorbed and the barrier which is there, and you have to overcome this to have the reaction, and that barrier is called threshold, and by observing the energy you overcome that threshold and the reaction will take place, is called the threshold reactions. And this happens for negative Q values. In negative Q value you need more energy, and this energy is used to overcome the barrier or the threshold. Then nuclear fission. Before that, there are some worked out problems. You can go through this. See, uranium-238 plus neutron is equal to uranium-3 to uranium-238 plus neutron gives rise to uranium-239 plus gamma. What could be the total energy of gamma radiation? Assume that the incident neutron energy is negligible. So here is the solution. You can go through this. The reaction specified is radiative capture, where 239 uranium de-excites by releasing gamma. So we can go through this and understand. It is in the screen.
Audio is not audible.
Have you gone through the problem?
Yes, sir.
Okay. So let us have the next part, that is nuclear fission. In nuclear fission, you also encounter the radioactivity. In fission, a heavy nuclei splits into two smaller nuclei are called fission fragments. And every fission event is accompanied by release of energy. And it is around 200 mega electron volt. 1 eV is equal to around 1000 Kelvin, 11,000 Kelvin. 11,000 Kelvin. So, a few neutrons, beta, gamma, and neutrinos are also released. In most fission events, only two fission fragments, one heavier than the other, are released, and it is called binary fission. The probability of release of more than two fragments or release of equal fragments is called symmetric fission, and its probability is very low. A heavy nuclide in this context refers to an actinide, that is atomic number 89 and above, and all such nuclides, lanthanides and actinides, is placed in the lower side of your periodic table.
Periodic.
Lanthanides and actinides, so I am referring actinides, atomic number 89 and above. And all such nuclides are radioactive with specific probability for fission and is called spontaneous fission. The probability of fission is enhanced millions of times when a heavy nuclide is agitated by the collision of a particle. In a reactor, the fissions are caused by neutron absorption in a heavy nuclei, and the examples are uranium and plutonium fission. And these are called neutron-induced fission, as a neutron is involved in the fission reaction. And it is shown in the picture. There is a neutron, your uranium or plutonium nuclide in the reactant space. Then your compound nuclei is formed when neutron is absorbed by the uranium or plutonium nuclei. Then it disintegrates due to unstable, as it is unstable, it disintegrates or splits into fragments and release energy around 200 mega electron volt. And you have a fission product 1 and 2 and 3 neutrons as shown in the picture. And the reaction is like this: neutron plus uranium 235 forms the compound nucleus uranium 236, and your barium 139, krypton 94, and 3 neutrons are being created as a fission product or fragments, and 200 mega electron volt energy is being released. Similarly, if you bombard plutonium with neutron, then neutron plus plutonium 239 will give you the compound nucleus plutonium 240, and it will be disintegrated into xenon, zirconium, and 3 neutrons and 200 mega electron volt energy. And this can be explained in liquid draw model as shown in the figure. So fragment separation, potential energy. So the curve is shown in the screen. Nuclear and Coulomb's interaction, then Coulomb, then critical energy, fission barrier, and fission energy. So here are the fission is said to be a mode of radioactive disintegration. So whether it enhances the stability or not is explained here. Critical energies for fission is shown in the tabular form for thorium, for uranium, for plutonium, so on and so forth. The threshold energy and endothermic reaction or threshold reaction. Then odd even effect. What is it? The addition of a neutron would change the number of neutrons from odd to even or even to odd. So in uranium, how many neutrons are there? in this reaction, you can see here you have 92 number of protons and 143 number of neutrons. Here there are 94 number of protons and 145 number of neutrons. So here 145 and here 143 number of neutrons. So these two are odd numbers. So when neutron is bombarded, here you can see uranium-236. So how many number of neutrons? Initially in uranium, you have 143 number of neutrons, and after the neutron is being bombarded and compound nucleus is formed, 144 number of
144.
neutrons in compound nucleus. So from odd to even transition, odd number of neutrons are there, and in the compound nucleus there are even number of neutrons. Similarly, in some other reaction, there will be even number of neutrons, and after the neutron is being bombarded, there will be odd number of neutrons. And pairing effect, and in Wijaker semi-empirical mass formula, you have a term delta, plus minus delta, pairing energy in the binding energy formula. So with a Z fixed, that is 92, when the neutron number is even, the pairing term is positive, even, and gives more binding energy to the nucleus than when neutron number is odd. This energy is available as excitation energy in the compound nucleus when formed. The compound nucleus de-excites by releasing this energy. One of its de-excitation mode is fission. Uranium-235, when it captures a neutron, becomes uranium-236, which is an even nucleus. Even number of proton, even number of neutron. Has a higher energy to be released. When uranium-238 captures a neutron, it becomes uranium-239. Then uranium-239, even number of proton, odd number of neutron, even odd nucleus, has less energy to be released. In other words, an excited even compound nucleus would disintegrate more readily than an excited even odd or odd even compound nucleus. So uranium-236 is an ideal candidate for fission than uranium-238. When we refer to the fission of a given target nucleus, we imply the fission of corresponding compound nucleus. This is the reason why uranium-235 fissions readily, irrespective of incident neutron kinetic energy. Unlike 238, that shows a threshold, and you energy external energy, and you need a endothermic reaction so that the fission will take place, or threshold reaction. This explains the relevance of even or even odd status of nucleons in the context of critical energy of the fission. So in threshold reaction, you need external energy, and it requires more energy from some other source. But in spontaneous fission, you do not need any energy, and you will also get energy that is of the order of 200 mega electron volt. Then fission fuels. All nuclides in the actinide mass range undergo neutron-induced fission with different probabilities and thresholds. Only a few of them individually or in combination are suitable to be used for reactor as a fuel. Consequence to the interaction with neutrons and radioactivity, isotopes of actinide grow in number and variety. Several of these isotopes, though not intended as fuels, could also undergo fission in a reactor. And what are the nuclear fission fuels? Uranium, thorium, these are nuclear fuels. Plutonium, okay, they readily disintegrate. Then fission products. Fission product for fission in uranium-235 is shown in the figure. So here it is a binary fission, that is two fission fragments are released. They carry about 80% of the fission energy and hence are energetic. You can see in the screen. They are highly excited and unstable and so disintegrate through alpha, beta, gamma or neutron emission modes. Fission fragments and those resulting due to their radioactivity are collectively called fission products, FP. While the fragments are positively charged excited nuclei, some of the fission products could have also include acquire an electron to become neutral atom, and fission product will also include those fragments that have transmuted to stability as shown in the figure 2.3. For a given energy of neutron, the excited compound nucleus uranium-236 could split in many ways. The products are generally in the mass range 65 to 170, each product having almost definite probability of being produced. This probability is given the fission product yield, which varies as the so-called AM curve, as shown in the figure 2.3. It may observe that as neutron energy increases, a tendency to favor symmetric fission increases, indicating that at much higher energy, say about 100 mega electron volt, the portion in the M curve would disappear with symmetric fission mostly favored. The curve and its features grossly are similar across different fissioning nuclei, but with the maxima shifting slightly to the right as the fissioning mass increases. This yields per fission sum to 2, since each fission gives 2 products. Binary fission, 2 products. Then asymmetric fission, the fission products are having different mass number. Then fission cross section with energy is shown in the screen. For uranium 233, 235, 239, and thorium 232. And in tabular form, you can see the fission energy distribution for uranium 233, 235, 239, plutonium, 238 uranium, and 232 thorium. So you can see distribution of fission neutron energies versus normalized fission spectrum. So it is a peaked curve. It peaks at E dash is equal to T by 2, you can see, and it is around 700 kilo electron volt, and it is in logarithmic scale in the screen, and the average is around 2 mega electron volt. Prompt and delayed neutron. So the average number of neutrons emitted for fusion or prompt and delayed neutron are shown in the table, and it can be explained for nuclear safety. So how to design a nuclear reactor? You know, this is the fission process in pictorial form, and how neutron multiplies in a reaction. And there are 2 types of neutrons, slow neutron and fast neutron. The cross section are higher, often by several order of magnitude at low energies than at higher energies. For the fissile nuclide, the fission cross section are a few hundred times higher at the sub energies than in kilo electron volt, mega electron volt range. This is the main reason behind the idea of slow neutron reactor. The light material used to slow down neutrons are called moderators. These moderates or slow down the neutron. The moderators eventually thermalize the neutron, hence slow neutrons reactors are called thermal reactors. However, the capture cross section are also higher for the slow neutrons, and the choice of energy region depends on the fission to capture ratio of the fuel. Since fission rate must be larger than the capture rate to maintain the desired neutron population, giving due allowance to neutron losses. From the cross section data, it has been found that the fission to capture ratio of the common fissile nuclides are more than unity. The ratio supports critically for the neutron energies below 1 electron volt, even with a small percentage of fissile content in the fissile fertile mixture, suggesting the feasibility of slow neutron reactors. A reactor is also feasible with fast neutrons with energy of a few hundred kilo electron volt, provided the fissile content is increased well beyond 10%. These facts could be verified by observing the calculated fission to capture ratios at different energies for different fissile or fertile proportions. The only fissile matter that occurs in nature is uranium-235, but its abundance is only 0.7% in natural uranium. Therefore, economy of fissile material is of utmost importance. Enriching the fuel with this fissile material would deplete it faster. Fortunately, data proves that the slow reactor is feasible with the natural uranium, that is 0.7% uranium-235 and 99.3
Excuse me,
uranium
sir.
238. This gives the reason why slow reactors have achieved prominence over fast reactors. Most of the reactors in operation in world are thermal neutron reactors. As the neutrons are very fast at birth, they need to be slowed down to sub-electron volt range to realize a thermal reactor. This is achieved by adequate quantity of light materials like your heavy water or normal water or graphite, etc., as moderators in the reactor core, along with the fuel. Multiple scattering with these moderators, nuclides slow down the neutrons to the thermal energies. Most fission in thermal reactor happens below 1 electron volt. Fast reactors, on the other hand, operates with neutrons above 10 electron volts, with the peak flux near or above 100 electron volt. A fast reactor has no moderator but requires fissile enrichment well beyond 10%, 15 to 30%. Okay. Then
Sir,
kinetic properties.
fissile, excuse me, sir. Sir,
हाँ
fissile
बताइए क्या
materials
आपको
means
समझ में नहीं आया? So
fissile
there are
materials means
two types of reactors. One where there are moderators in form of your graphite or heavy water or etc., where the neutron is slowed down and becomes around 1 electron volt. But in some other reactor which has very small number all around the world, there you do not need slow neutrons. So the electron energy is around 10 electron volt or 100 electron volt. And there are two types of reactors. In one reactor, the neutron energy is around 1 electron volt, and these are thermal reactors. And the fast neutrons constitute the other type of reactor where neutron energy is around 100 electron volt or 10 electron volt. Are you getting it?
no, sir. What do you mean by fissile material? We didn't understand.
Fissile material means the material which can be used for fission reaction. Uranium is a fissile material. Thorium is a fissile material. Plutonium is a fissile material which can undergo radioactive disintegration, and fission reaction can be possible with those of type of reactors, those type of materials. Iron cannot be a fissile material. Nickel cannot be a fissile matter. Carbon cannot be a fissile matter. You cannot use these things, these materials in a nuclear reactor for your fission reaction. Are you getting it?
Yes, sir. Clear.
Okay. Then resonance escape probability factor. Resonance capture escape of slowing down neutrons as shown in the screen. The fast neutrons get slowed down in the moderator and ultimately thermalized. As we have discussed in a thermal reactor, the thermalization is achieved in several collisions depending on the moderating material. And the moderating material we usually use is heavy graphite or heavy water. A heavy water plant is there at Talcher. So these the several collisions takes place with this moderating material, crossing the intermediate energies in each collision, and the intermediate energy includes the energy range wherein the resonance absorption of fuel mixtures, mainly uranium-238, occurs. Every collision with the moderator results in slowing down, but every collision with 238 uranium finds the risk of being lost in capture. And some of the neutrons are lost in resonance absorption in uranium-238, or even neutron and nucleus number, and so also the pairing energy is like less. So on the way through thermalization, so resonance capture or escape of the fast neutrons undergoing repeated collisions, losing energy in each collision. When the neutron emerges with its energy under the capture resonance, it is absorbed. And then your thermal utilization factor. The thermal neutrons that are absorbed in the fissile fuel only can cause thermal fission, and your thermal utilization factor F can be evaluated using the formula sigma fuel A divided by sigma fuel A plus sigma moderator A plus sigma structure A plus so on and so forth. And heterogeneous thermal reactor core, the moderators and fuels. The fuels are embedded in the moderator as shown in the screen. Then non-leakage probability, effective neutron multiplication factor can be calculated using the formula eta sigma pf p superscript f subscript nl p superscript t subscript nl. This is also called a 6-factor formula. Then reactor power can be calculated using the formula EF integration sigma F phi dP. And then your fuel burn up and consumption. So for fuel burn up B can be calculated using the formula PT divided by N, T in days and M in tons. Similarly, you can calculate B in atom percentage as sigma J Nj sigma Fj phi T by sigma J Nj multiplied by 100 in percentage form. So you need, for designing of a nuclear reactor, you have to well uh, acquainted with some basic things: fuel composition, moderator, coolant. When it is a thermal reactor, it will heat up. So you need to cool it. So coolant are being used, and your some salted water is one of the coolant used in India, and there are many good coolants than like liquid nitrogen and others used by different liquid sodium, liquid nitrogen. So these are also used as coolants, and your salt water is also a very good coolant. Then reduced leakage control, structural material, clad for holding the fuel, as piping for coolant and control rods, and as the reactor vessel for supporting all the reactor components. So these must be neutronically compatible. That is, their interaction with the neutrons must not have adverse impact on the reactor performance. And these material must be capable of withstanding high temperatures for prolonged time. Zirconium, aluminum, stainless steel are such type of material. The choice of materials, their composition and quality depends on the reactor type and power level. How much power you expect and which type of reactor you are going to design. Then types of nuclear reactor. So this is the silent stage of electricity producing using a nuclear reactor. You have fresh fuel, you can have it in the reactor, then the fuel is spent out, and reprocessing and useful fuel for reuse and waste for disposal. And from the reactor you have heat, thermal energy, then steam generator. The thermal energy will form a steam, and this steam will rotate the turbine, and electricity is produced and power is distributed thereupon. So there are different types of nuclear reactors, neutron energy range. So your thermal reactors and fast reactors, which I have explained earlier. In thermal reactors, you have 1 EV or smaller neutron energy, and in fast reactors, 10 kilo electron volt or 100 kilo electron volt or more neutron energy. And moderators, core arrangement, size, purpose are shown in the tabular form in the screen. Then strategic civilian reactor and military reactors. Civilian reactors are used for electricity production, and the military reactors are fissile material production for atom bomb or nuclear bomb production. Then generation 1 reactor, generation 2 reactor, generation 3 reactor, generation 4 reactor. Generation 1 reactor are early prototypes, research reactors, non-commercial power reactors. Generation 2 are most current nuclear power plants. Generation 3 are based upon acquired experience, and Generation 4 advanced technology still under development for different nations. Then energy variation of fission to capture ratio for natural uranium. In the x-axis you have energy, in the y-axis fission to capture for natural uranium. Thermal reactor, it's thermal part, and this is fast part. So fission to capture ratio of different fuel compositions are shown in the tabular form. Okay, so you can see here a thermal reactor. The schematic of a thermal reactor, the reactor vessel, then the first valve is having the coolants and coolant entry points, coolant piping, then fuel is there in a rod form, then moderators, then hot coolant out, then control rod, then reactor shield, containment structure, and fast reactor you have only fast neutrons, but the picture is very similar. And fast breeder reactor, there is fertile blanket, fissile fertile core, and shield. There you do not need any coolant or moderator. or you do not need moderator to slow down the neutron, and it happens very fast. So this is primary and secondary sodium circuits in the fast reactor, as shown in schematically in the screen. So this is flux density variation with energy in thermal and fast reactor in a non-elastic collision type. And India has a nuclear program, very successful nuclear program. So stage 1 runs several thermal reactors with uranium-235 and 238 accumulated converted to plutonium-239 for starting fast reactor. In stage 2, we have run several fast breeder reactors with plutonium-239 and plutonium-238. Irradiate thorium-232 in the blanket to produce uranium-233 and accumulate. In stage 3, we have our thermal breeder reactors and fast breeder reactors. So there are some power plants in India. Tarapur Atomic Power Plant having a capacity 1400 megawatt. Rajasthan Atomic Power Stations 1180 megawatt energy from producing unit. Madras Atomic Power Station, Tamil Nadu 440 megawatt. Kaiga Generating Station, Karnataka 880 megawatt. Kadankulam Nuclear Power Station, Tamil Nadu 2000 mega electron volt capacity. Narora Atomic Power Station, Uttar Pradesh 440 mega electron volt megawatt power. Kakrapur Atomic Power Station, Gujarat 1840 megawatt power is we get from this power station. So in total, we have 24 units and around 8,000 megawatt energy is being obtained from all these power plants. Okay. So we shall discuss the rest in the next class. Okay. Thank you.
Okay.
Thank you, sir. यार पीडीएफ छाड़ लगे मैडम और 2 पेज पीडीएफ
हेलो एक्चुअली एक्चुअली मटेरियल साइंस MPHE 025 टा हवा कथा क्लास 3 दिन अच्छी माने चेंज हे कि देखुली किंतु 2 6 जो रिएक्टर के कितना कर
Material science हवा कथा है न्यूक्लियर फिजिक्स
हां हां
ସାର୍ଙ୍କର ଦିଟା ଅଛି ସେମ୍ ଅଛି ସେଥିପାଇଁ ସେ ଏଇଟା ବୋଧେ ପଢେଇ ଦେଲେ ଆଗ ମୁଁ ପଚାରିବା ଥିଲା ଯେ
ସେଟା ସରି ଯାଉ ଆମେ ସାର୍ କହିବା ଯୋଉ ଆମର ଅଛି MPHE 025
ମୁଁ ଏବେ କହିବି ବୋଲି ସାର୍ ପଳେଇଲେ
ହଁ ପଢେଇଲେ ସେ କାଲି କହିବା ଆମେ ନହେଲେ ଆଉ ସେଟା ସରିଗଲେ ସେଟା ପଢିବେ ଆଉ କାହିଁକି ସେ ମେଟେରିଆଲ ସାଇନ୍ସ ଟା ବୁକ୍ ଫୁକ୍ କିଛି ନାହିଁ ଆଉ ସେଟା କେମିତି କଣ ପଢିବା ଯଦି ସାରଙ୍କର ବୁକ୍ ବି ଥିବ କିଛି ସେୟାର କଲେ ଭଲସେ ଜାଣି ହବ
ମେଟେରିଆଲ ସାଇନ୍ସ ର ଲିଙ୍କ ଖାଲି ଅଛି
ହଁ ସେ ଦେଖିବ ସାର୍ କାଲି ପଚାରିବ
ଷ୍ଟାର୍ଟିଂ ରେ କଣ କହିଲେ ସାର୍ ଡାଇରେକ୍ଟ ପଢେଇ ଦେଲେ ନା କିଛି କହିଲେ
ନା କିଛି କହିନାହାନ୍ତି ଡାଇରେକ୍ଟ ତ ଷ୍ଟାର୍ଟ କଲେ ଆଉ
ସାର୍ଙ୍କୁ କହିବା କି ଏମିତି ଗାଈ ନଉଛନ୍ତି ନ ନେଇକି କିଛି ବୁଝେଇବାକୁ ଗାଈ ନେଲେ କିଛି ହଉନି
ହଁ ନେ ଦେଖି କଣ କି ଖାଲି ନହେଲେ ଆଉ ଦେଖିବା କହିବା କାଲି ଆଉ
ନା ସେ ଗାଈ ନଉଛନ୍ତି ଯେ ବୁଝି ହଉଛି ନା କିଛି ପାଠ ପଢେଇଲେ ଆମକୁ କିଛି ହେଲେ ବୁଝା ପଡିଲେ ଚଳିବ ପୁରା ଗାଈ ନଉଛନ୍ତି ବୁଝି ହଉନି ଅଧା ଏଇଟା ଟିକେ ଚଳିବ ଟିକେ ଟିକେ ବୁଝି ହଉଥିଲା ହେଲେ ଫିର ବି ତ ଅଧା ବୁଝି ହଉନି ନ
ଏଇଟା
ବୁଝେଇଲେ
ଆଗରୁ
ଖାଲି
ପଢିଦେଲେ
ଆମେ ତ ସେମିତି ଏକା ପଢିପାରିବା ସାର୍ ଯେମିତି ପଢି ଦଉଛନ୍ତି ଆମେ ବି ପଢିପାରିବା ନା
ହଁ ହଁ ନା ଠିକ
ଖାଲି
ଅଛି
ଗୋଟେ
କିଛିଟା ଇମ୍ପୋର୍ଟାଣ୍ଟ ଯୋଉଗୁଡା ସେଗୁଡା ଟିକେ ଭଲସେ ବୁଝେଇଲେ ହେଇଯିବ ସେଗୁଡା ସବୁଗୁଡା ପୁରା ସ୍କିପ୍ କରିକି ପୁରା ପଢେଇ ଦଉଛନ୍ତି ପୁରା ଛାଡିକି ଖାଲି ଇମ୍ପୋର୍ଟାଣ୍ଟ ଗୁଡା
ହଁ ନା ସେ ଇମ୍ପୋର୍ଟାଣ୍ଟ ବି ଟିକେ ଭଲରେ ବୁଝାନ୍ତେ ବୋଲେ ହୁଅନ୍ତା
ହଁ ହଁ
ସେଇଟା ବି ଖାଲି କହିଦଉଛନ୍ତି ଆଉ ଖାଲି
हाँ
ହଉ ଦେଖିବା ଆଉ ସେଇ ଅଲଗା ସାର୍ ଆମର ସେ ମ୍ୟାଡାମ 2 ଜଣ ସେ ଇଏ ମ୍ୟାଡାମ ଯୋଉ ପାତ୍ରୀ ମ୍ୟାଡାମ ତାଙ୍କ ନାଁ କଣ ସିଏ ଟିକେ ଭଲ ବୁଝଉଛନ୍ତି
ପ୍ରାକ୍ଟିକାଲ କପି ସବୁ ଲେଖିଲଣି?
କୋଉଟା
ପ୍ରାକ୍ଟିକାଲ କପି
ସୁନନ୍ଦା ମ୍ୟାଡାମ ପାଇଁ PDF ସେକେଣ୍ଡ ଟା କାଇଁ ଦେଲେ ନାହିଁ ଆଉ।
ନା ସେ ମ୍ୟାଡାମ ଗୋଟେ ଏକା ଦେଲେ ଆଉ କିଛି ଦେଲେନି ଏବେ ତାଙ୍କର ଆଉ ଗୋଟେ କ୍ଲାସ ଅଛି ତାଙ୍କୁ କହିବା ଆଉ ଗୋଟେ କଣ ନାନୋ ସାଇନ୍ସ ଅଛି ଲାଷ୍ଟ
ଆଉ ସାର୍ ଙ୍କର PDF ଗୁଡା କାହିଁ ଗୋଟେ ହିଁ PDF ଅଛି ଆମ ପାଖରେ। ଏ ସାର୍ ତ
କେହି
ପଢେଇଲେ
PDF
ଏଇଟା ଗୋଟେ ନାହିଁ।
ଦେଇନାହାନ୍ତି ସବୁ ତ ବୁକ୍ସ ରୁ ପଢଉଛନ୍ତି ଆଉ ସବୁ ଇ ବୁକ୍ ରୁ ପଢଉଛନ୍ତି ବୁକ୍ ରୁ ପଢଉଛନ୍ତି ସ୍କ୍ରିନ୍ ସେୟାର କରୁଛନ୍ତି ଖାଲି ସୁନନ୍ଦା ମ୍ୟାଡାମ ସେ କଣ PPT ବନଉଛନ୍ତି ଗୋଟେ ହିଁ ଛାଡିଥିଲେ ହଉ ଦେଖିବା ଆଉ ପଢିବା ଆମେ ଏକ୍ଜାମ ଦେବା ଆଉ କଣ ଯାହେଲେ ତ କିଛି ବୁଝି ହଉଛି ଯେ ଏଇ ଯୋଉ ଫାଷ୍ଟ ଷ୍ଟାଟିଷ୍ଟିକାଲ ମେକାନିକ୍ସ ପଢେଇଲେ ସାର୍ ଆଉ ଏଇ ସାର୍ ସେମ୍ ପଢଉଛନ୍ତି ଖାଲି ଗାଇ ନଉଛନ୍ତି ସରୋଜ ସାର୍ ଆଉ ସୁନନ୍ଦା ମ୍ୟାଡାମ ଟିକେ ଭଲ ବୁଝଉଛନ୍ତି
ଟିକେ ପଏଣ୍ଟ ସେମାନେ ପୁରା ହିଣ୍ଟ ସାଥିରେ କହୁଛନ୍ତି ଆଉ ପଢେଇ ଯେମିତି ନର୍ମାଲ କେହି ପିଲା କିଛି ଜାଣିନାହାନ୍ତି ସେଇ ହିସାବରେ ପାଠ ପଢେଇବା।
ହଉ ଦେଖାଯାଉ ହଉ କ୍ଲାସ କରିଦବା କଥା ଆମେ କିଛି ତ ହେଲେ ବୁଝା ପଡୁଛି ଆଉ
ହଁ ମାନେ
ଆମେ ଘୋଷାଡିବା କଥା କିଛି ତ କରିପାରୁନେ।
10%
ଜଣା ପଡିଯାଉଛି।
10% ଟିକେ ବୁଝିଲେ ନିଜେ ଆଉ ଟିକେ ପଢିବାକୁ ହେଇଛି ଆଉ
ହଁ ଇଣ୍ଟରେଷ୍ଟ ଆସିବ ଟିକେ ପଢିବା ପାଇଁ ଆଉ
ଯେ ଆଉ ଟିକେ ଇଏ ସାର୍ ଟିକେ ଆଉ ଟିକେ ଏକ୍ସପ୍ଲେନ କରନ୍ତେ ଯେମିତି ସରୋଜ ସାର୍ ହେଲେ କି ମ୍ୟାଡାମ ହେଲେ ଟିକେ ଏକ୍ସପ୍ଲେନ କରିକି ଯାହାହେଲେ ପଢଉଛନ୍ତି
ହଁ ହଁ
ଠିକ ଅଛି ସିଏ ମାନେ କଭର କରୁନାହାନ୍ତି ବାକି ପଢଉଛନ୍ତି ଆଉ
ସାରଙ୍କୁ ଆମେ କହିବା ସାର୍ ଯେତିକି ସରୁଛି ସରୁ ଟୋଟାଲ ସାରିବା
102 ପେଜ ପଢେଇଦେଲେ ବା 102 ପେଜ।
ହଁ ସ୍କିପ କରିକି ବି ପଳେଇଗଲେ 4ଟା ୟୁନିଟ୍ ପୁଣି ଟାଇମ ହେଇନି ଟାଇମ ସରିନି ଆହୁରି 8:30 ଅଛି 8:05 ରୁ 10 ରୁ ଛାଡିଦେଲେ ହଉ ଦେଖିବା କାଲି କ୍ଲାସ କରିବା ସାର୍ ଯଦି କାଲି ବି ଏମିତି ପଳେଇବେ ପଢି ଦେଇକି ମୁଁ କହିଦେବି ଆଉ ସାର୍ 8:30 ତକ ଏଟଲିଷ୍ଟ ଟିକେ ଆହୁରି କୋଉଟା ଟିକେ ଏକ୍ସପ୍ଲେନ କରିକି ପଢାନ୍ତୁ କହିବେ ଆଉ କଣ ଏମିତି ପଢିଲେ ହେଲେ ବେଶୀ ସବୁ ପିଲା ଅଧା ପଳେଇ ଯାଉଛନ୍ତି ହଁ ଠିକ ଅଛି ବାଏ ବାଏ
ଭାଇ ଗୁଡ୍ ନାଇଟ୍।
ଗୁଡ୍ ନାଇଟ୍